top with you, and then you won't be able to see my smiling face so much. There. Okay, so hang on one sec, and we start. Great. You're in this. Maybe before I get started, we can just get a confirmation. Someone can check on the Google Hangout that confirms that you are seeing what I am seeing. Ah. Falls into it's. So with that in mind, let's get started then. This is going to be a somewhat unusual sort of talk. Unusual in that it's not quite a typical PowerPoint sort of thing. We're going to do some experimental stuff with trying to write on the screen. Hopefully this will work. This is the flow-MINCUT theorem and other results in network flow optimization. What I'm going to be doing is talking very briefly. Oh, sorry, Sanjeevi, I just cut your name out. There we go. Oh, good heavens, and now my pen controls are not working. Problem. Hang on a sec, let me see if I can fix that. Deuce. It turns out that our wonderful software has disabled the hacks that I programmed. Let's see if we can get this to work anyhow. What I'm going to be doing is talking about a recent paper that KRISHNAN has put on his website. You can find it here. You can also find it showing up on the archive as of tomorrow concerning workflow optimization. Look with the classical result that inspired this. This is the MAXFLOW-MINCUT theorem. And it's as follows. Let's say that you have a network that is a directed graph that is, for our purposes today, directed acyclic. That is, have some source out of which edges come, some target into which edges go. And from that, you look at a flow over the network. So assign certain numbers to the edges, and what you need to have is conservation. So let's see, if you had 3 units of flow coming in here, 4 units of flow coming in here, you'd have 7 units of flow coming out there. Now there are constraints or capacities associated to these edges. What these do is they constrain how much can come. So for example, this guy down here would be illegal because the maximum amount of flow you can have on this edge is equal to 5. What you want to do is put a maximal flow. I mean, a flow that maximizes either the net amount coming out of the source or the amount into the target. And the classical theorem that starts all of this has to do with cuts and dual notion. A cut is a notion of edges that sets the from target. The value of a cut is equal to how much capacity comes with each edge located in the cut. So this cut would have value of 13. And what I'm going to do, to make this a little bit more topological, is a feedback edge that goes from the target back to the source. This is going to be assumed to have infinite capacity. Now to do that, the result that gets things started is the following result of Ford and Fulkerson had their antecedents, as we'll talk about, is that the maximal flow value is equal to the minimum cut value. So what you do is look across all cuts of this network at the associated cut values and the minimum of those. That gives you the maximal amount of flow that comes through the graph. There's a little bit of history associated with this. coming in from MVJ saying we are restricting to only single source, single sync graphs right now. The answer to that is yes. As drawn. Okay, a little bit of history here. In the 20s, the primitive version of this result, known as Menger's theorem, which counts the number of connected paths from one vertex in a directed graph to another. When you get up to the 50s, that's when we have the real MAXFLOW-MINCUT theorem. And for this, in conjunction around the same time as some other folks independently, with that came some algorithms that a huge amount of impact for Fulkerson's work was directly inspired by applications, transportation networks, and other things. This result has gone to be a cornerstone of optimization theory. In fact, one of the best ways to prove it quickly and easily is to use standard duality in your programming to write down and dual problems, between flows and cuts, respectively. Now, the literature on this subject is absolutely huge. There's an enormous number of different perspectives with to attack this problem. Among the more interesting ones would be matroids. I think this is from the 1970s or so. I can't remember who did matroid duality. Please forgive me. In the 80s, we get a very algebraic version of this due to freeze. It works for totally ordered commutative monoids with some cancellative properties to them. What I'm going to be talking about today is a far-reaching generalization of the result of freeze. If move the clock ahead a little bit, skipping over a lot of algorithmic and computational complexity work associated with this result, what we get to is some work that I did with Yasu Hiraoka, trying to reinterpret the MAXFLOW-MINCUT theorem topologically. And what we did was use sheaves over the networks, where instead of a capacity of 6, what we did was put vector space of dimension 6 over the edge, and a vector space of dimension 7 over the edge. And then we built a topological data structure, a sheaf, something like a representation of this graph in the category of vector spaces. And then our work showed that MAXFLOW-MINCUT was really related to a long exact sequence in cohomology. The details about that, you can see chapter 9 of the book that I am writing on algebraic topology. If you go to the appropriate website for that course, then you can check out right there. Chapter 9 will have a bunch of details on that for you. There's been some work, Bachman in particular, just recently showed algebraic geometry approach to MAXFLOW-MINCUT using Riemann-Roch theory. I've skipped a bunch of other relevant work for which I apologize and can only say that there's a finite amount of time and space on this slide. Talk a little bit about the topological approach to this and why I think that sheaves are really the relevant tool for understanding or addressing this. If you think about your graph or your network as a space, then it has a structure of a cell complex where we have vertices and we have edges. Now that cell complex can be thought of a category where the objects are vertices and the edges, of course, and we have nice morphisms from the vertices to the edges. We're going to sheaves for the rest talk, and in particular, cellular sheaves, by which I mean that go from X, thought of as a cell complex in this way, to some category of data. In the way that he and I did with the MAXFLOW-MINCUT theorem, this category of data with categories or some field. There is, of course, a lot of other interesting data that one could put over the edges. In particular, what I'm going to use for the rest of this talk is a somewhat different and kind of that hasn't been used very much in applied topology or not applied topology. Here's the idea. It starts from the high-level view that this duality between flows and cuts is really a form of Poincare duality, but straight up Poincare duality, because we have to worry about all of those capacity constraints, all of the cut values, all of the flow values, etc. This duality is really a form of Poincare duality on sheaves. And it's really a brilliant work of KRISHNAN that unfolded this simple observation and idea into something that's really quite powerful. All right, here's a high-level view of what is happening inside of a sheaf-theoretic version of the MAXFLOW-MINCUT theorem. The this. When you look at the problem, consider the capacities. These capacities are best encoded as a sheaf over the space, over the graph. Now, what do I mean by that? Well, in the particular case of the classical MAXFLOW-MINCUT theorem, the sheaf is a sheaf of semi-modules. Now, that is in a minute. The simplest example of this expands these numerical capacities out to intervals. For example, in the capacity of 6, we have the closed interval from 0 to 6 under addition, but it's going to be an unusual sort of addition in that there are no inverses, there's no subtraction. So you have something like a commutative monoid. It's going to be important to keep everything commutative so that we don't care about which order things are added, but it is also restricted or partial in the following sense. You can add with the interval until you get up to 6. And if you try to exceed that, addition is no longer possible. That's a code. Okay, what exactly do I mean by semi-modules? This is not a standard term in literature. In particular, what I mean is partial commutative monoids. So again, monoids meaning that there are no inverses allowed. You can only go forward. Commutative, I think everyone knows what that means. This is like an addition. And partial means that you can't always add two elements together. In particular, if you violate the constraint bounds, then it is no longer defined. It's a little bit more complicated than this, because we're going to need a partial semi-ring, we will refer to as S. A canonical example of this is going to be the natural numbers, where this has all the usual structure of the ring of integers, Z, except that it's a semi. You can only go forwards and not backwards. And given that semi-ring, we're going to look at monoid objects in the category of partial commutative monoids. Now, that's that's a lot of stuff that's going on right here, but you're going to have to stick with me. It really does become necessary and important. Here's the definition. A semimodule is going to be a module object over this partial semiring S. So what you do is think of it as a partial commutative monoid where your scalar multiplication is multiplication in this semiring. Now, sounds pretty scary and indeed give one a headache, but for all intents and purposes, this thing is the natural numbers. Simple examples where the semiring is Boolean. Looking at, say, Boolean lattices over the semiring of true and false, but most of the time, it's just going to be the natural numbers. And the reason for that is that our graphs are all directed graphs. And this implicit notion of going forward, of orientation, that leads to working with the naturals as opposed to the integers. There's good news associated with that. The news is that there's a lot of algebraic preliminaries in order to get things to work. The goal is to use algebraic topology in order to reprove the classical theorem. That involves looking at sheaves and all the things that you can do with sheaves, namely sheaf cohomology, co-sheaf homology, and all the other wonderful algebraic topology. Unfortunately, homology, taking values in semimodules, is not standard stuff. So what we're going to do is fix a partial semiring, work in a category of partial commutative S semimodules. Again, if you away, just think, oh, everything is going to take values in 0 to some number, some capacity. That's a particularly good example. Of course, one go far beyond that, and that's where it gets interesting. But for the moment, just think about these guys as your semimodules. Now, a sheaf in our world today is going to be an S sheaf. That is a functor from your graph, thought of as a cell complex, to this category of partial commutative S modules. And one has to show that it has some relatively nice properties. There's a tensor product that works well in this category. Whenever I write that tensor product, it is going to be a tensor product over the semiring S. And from time to time, we assume that the semimodule that you're working with is flat, which means that it preserves equalizers. I'm not always going to be careful about saying when I assume flatness and when I don't, because I've got a finite amount of room on screen and in my head. You're going to want to see Sanjeevi's paper to get the full details. Let's see. Talk about the big picture. There's a lot of stuff that goes into this classical MAXFLOW-MINCUT theorem. And this is what we need to build in order to get this working. For capacities, what we're going to do is add a sheaf F that's used in these semimodules. That's exactly as we saw before looking at capacities in that simple example where we have those intervals under addition. Okay, so keeping that in mind, and that's going to be a sheaf on our network X. Okay, one of the annoying issues is that the edges are all directed. How do we encode that? We have to have sort of directedness to our sheaves. Sheaf cohomology that common. 2 is encoded a sheaf on X but really an orientation sheaf. Our definition of that is in a minute, but think of that directedness also being included as a sheaf. The cuts are the same in both the classical and the topological case. It's just a collection of edges that separate the source from target. Flows, as we saw, are something that feel homological. The conservation property, things in have to equal things going out, is going to correspond to a homology theorem, and lower one taking values in the sheaf. So we're going to use sheaf coefficients. Now, I haven't told you how we define that homology. That comes later. But you should keep in mind is that H-flow-1 feels like a conservation law. And when coefficients in a capacity sheaf, you're legal. You've automatically satisfied that constraint. Cut values are going to be that is viewed in H-1 of your network, again, with the proper coefficients. I'll say what that is a little bit later. The flow values are going to reside in an H-lower 0. And then the duality between cut values and flow values is going to be a honest-to-God Poincare duality on these various homology and cohomology theories in complementary dimensions, where, of course, it's just looking at a one-dimensional base space. The complementary dimensions are 0 and 1. All right, a high-level overview. It's time to state what the result is and then get down to the business of actually defining a few of these things. The relative theorem is the following. If you have a directed graph and you pull out a distinguished edge E, remember in the cartoon that we had before, we had our directed graph that was doing whatever it is it's doing. The distinguished edge E is the thing that goes from the target back to the source. Given that, if we have a capacity sheaf of semi-modules, this encoding our constraints, our capacities, then the theorem is the following. If we look at the flow values, F flows, by F flows, I mean flows that satisfy the capacity constraints on X. And we get those flow values at E. That means how much stuff is flowing through this edge. That equal to what? I'm going to look at the cut value of cut C. I'll take a particular cut. I'm going to take all cuts that are what we will call E cuts, that go back to saying what happens at this edge. Minimum. We're a categorical limit. And look at that. When I look at the flow values, this is really a max. It's really looking at all possible values. Now, this is a lie. This is not true. True. What I is not a limit, but a homotopy limit, or the appropriate structure. And that is where a subtlety in the theorem lies. Now again, what you should be thinking of is over here, on the left, you have all of your maximal, all your feasible flow values That's something like a maximum. On the right, we're taking a minimum of cut value. That's like a limit, or in this case, a homotopy limit. That's the sheaf theoretic version of the MAXFLOW-MINCUT theorem. So, of course, this wouldn't be any good if it did not recover the classical theorem, and indeed it does. You translate the results of the previous slide to that setting, then the set of all feasible flow values turns into a union where is a flow. And remember the semi-modules that we looked at with the classical setting. What one gets as feasible flow values is a semi-module that is the from 0 to value of that flow. I take the union of these intervals over all possible flows. Of course, at the right-hand side of that interval, what I get is the maximum flow value. Now, what the MAXFLOW-MINCUT theorem in sheaf theoretic version says is that I look at the cut value, in this case, the interval from 0 to the value of a particular cut, but instead of taking a minimum, what homotopy runs into is a plain vanilla limit in that simple setting, and that is precisely an intersection of these intervals. When I take all of those intersections, what I'm getting is a minimum over all cut values. So this is really nice. In what you're seeing is a categorification of classical result. If that this number happens to be equal to this number, its semi-module is equal to this semi-module. That is a much richer structure and very nice. Now, the statement of the sheaf theoretic MAXFLOW-MINCUT is somewhat obtuse, but it has, as presaged above, a very concrete corollary. Namely, that if your semi-module is based on a lattice, that is, if you have a semi-lattice ordering in your semi-modules, the graph is sufficiently nice. Let's say it's acyclic, except for the feedback edge. Then, whoops, for me, come back here. We can represent the sheaf theoretic MAXFLOW-MINCUT theorem a little bit more numerically as the following. We can take the join in the lattice over all flows of the value of flow on the feedback edge, E, and say that that is precisely equal to lattice theoretic intersection, or meet, over all cuts of the elements in the cut, all of the edges in the cut, of the weight of that edge. This is in the case where we have a weighted graph. So for each edge, we have a weight associated to it. And what we're seeing here is a numerical version of that called MAXFLOW-MINCUT theorem. It works in a much broader setting, in a lattice setting. The real solid theoretic MAXFLOW-MINCUT theorem is not numerical at all. It's categorical. It's on the level of semi-modules. This is the most general numerical version of it that's out of what KRISHNAN has done. Okay, look at a simple example of all that stuff. Here is something that is not numerical. The constraints are types. This is a Boolean sort of setting. Think of it this way. On each edge, you list which types of commodities are legal. So you can send commodities of type A or type B down the edge in quantity you want. I don't care about numbers. Just what is permissible. The question is, what can be sent from the source to the target? Well, if I just look at and say, well, you know, BCD here, ABC here, AD here, I have to take a lot of intersections over various paths. It's pretty clear that the only feasible value is A. That's it. That's the only thing that can be sent over this network. And that has to come down that path right here. That's it. That's the only thing that can be done. Now, here's the thing. If you start looking at cuts, you might be tempted to say, what is the minimal cut? Well, if I take these edges, then I'm putting together these, where in this case, addition is union, and intersection is the corresponding dual algebraic operation. So here I have AB, union ABC, union A. So the value of this cut is A, B, and C. If you look for the smallest possible cut, it's pretty clear that it's this guy, right down here. It has A and D. So the minimal value would seem to be A and D. And that leads you to suspect that it is called in the literature a duality gap between the maximal flow and the minimal cut. But is in error, because what you really want to look at is the feasible flow values thought of as something like a union. This is an intersection over all the cut values. And if I take that cut with A and D and look at all other possible cuts that I can get, well, this did before has A, B, and C. If the intersection of that with A and D, what do I get? D, and I'm with A. So in which the MAXFLOW-MINCUT theorem numerically, in terms of maximal flows and minimal cuts, it give you duality gaps. But think algebraically in terms of colimits, in terms of joins, that will give you a true duality. All right. Now, the theoretic result is extremely general. And that means to prove it, we need extremely general tools. And what I want to do for the remainder of this talk is show you what these tools are as a primer or an introduction to KRISHNAN's paper. The tool that's needed is a cohomology theory that respects these sheaves of semi-modules and that respects the orientation or the directedness of the sheaf. It's going to be defined implicitly as follows. A 0 of x, taking values in f, is to be defined like so. I hope I have enough room to write everything out here. I'm a little nervous about this. If you don't mind, I'm going to erase this and a little bit more compactly, putting in the coefficients directly. Let's see, h upper 0 of x is to be defined implicitly. I'm going to look at the direct sum of all of the sheaf values over vertices, and to look at all of the sheaf values over edges. Think of these as zero cochains and cochains, and have a pair of coboundary maps. What are coboundary maps? They're going to be induced by the sheaf restriction maps, where these are boundaries of the edges, but not one, but two maps given by the positive boundary and the negative boundary induced by the orientation. E0 is something like the kernel of this pair of maps. Of course, we're not in a nice abelian category, so we can't use kernels. What are we going to use? We're going to use the equalizer of diagram. And likewise, to define H upper 1, this did sheaf cohomology, we're going to use a co-equalizer. So we can't talk about a co-kernel. All right. Well, that's a start, but that is not the cohomology theory. Wait, that's not the cohomology theory you're looking for. Theory that is really needed in order to make this work is a cohomology with compact supports. And that is defined in terms of a colimit of the ordinary in this sheaf. Oops. Oh, no, that is not what I wanted. Come back. Where's my answer? There we go. The technical difficulties. So what I need to do is look at a colimit of sets of that complex and then the ordinary homology. X, the appropriate pullback sheaf. Okay. Well, does this actually make sense? This is not a standard sort of way to build cohomology. If everything is nice, that is, if instead of a semi-ring, you have a ring that agrees with the ordinary supported cohomology, it really is topological in the sense that it's invariant with respect to subdividing the graph. It's got a lot of nice properties, including the requisite functoriality, and what is going to be used. But we don't stop there. KRISHNAN defines a homology that is, in a sense, dual to this. It, too, is defined implicitly in terms of equalizers and co-equalizers, and is done at the level of a closed or Borel-Moore type homology. So again, what we do is we define H lower 1 to be an equalizer of the following diagram. Where I do is over the edges, I take the compactly supported zeroth cohomology of closure of the edge in the graph. Again, I look at a pair of maps that are based on the two different boundaries of that edge. That takes me to data that is stored over the vertices, and the corresponding co-equalizer that gives H lower 0 of, again, the closed or Borel-Moore type homology. As one would like, if we have a ring, then this gives us the standard Borel-Moore theory, which is good. Taking standard compactly supported sheaf cohomology, a co-sheaf homology closed, and updating it for coefficients in semi-modules. Now we get to the meat, which is where KRISHNAN has to prove all of the technical results. Let's go through those. This has to do with orientation. Remember I said that the orientation of the graph is encoded as a sheaf. It has the following local topology. It is H lower 1. Oh, I forgot to write that orientation sheaf evaluated at an element of the graph is going to be a local topology. So I look at what happens relative to the complement, and I take coefficients in S, where this again is my semi-ring, and thinking of that as the constant sheaf over S. That, with a little bit of investigation, turns out to be exactly what one would think an orientation sheaf looks like. It gives you the local correctedness of the graph. Then that one needs is some connecting morphisms to use a long exact sequence type argument for MAXFLOW-MINCUT. These connecting homomorphisms, plus and del minus, go from H. Let me that from H upper 0, completely supported of some closed set, taking views in the sheaf, to supported one-dimensional cohomology of X relative to that subset, again, values in that sheaf. There's also a version of a connecting homomorphism on homology, as well as cohomology, that here works with relative to some open subset U. New ingredient here is that there's two of them. There's not one of them. There are two, because you have the forward connecting morphism and the backward connecting morphism. That's a little bit of a pain. There are some other technicalities having to do with exactness of these homomorphisms. Be careful. Don't play with these at home, kids. Go check out some SHEAVES to get the full details. The duality result sticks all of these things together into a theorem that tells you that your H upper 0, completely supported on a of a set with your capacity sheaf tensored with the orientation sheaf, like you do in standard Poincare duality, is isomorphic to an H lower 1 of X relative to that subset U. Again, coefficients in the sheaf. Wait, that's not all. There is also equality between H upper 1 of a relative, again with local tending with the orientation sheaf, and H lower 0 closology, coefficients in the sheaf. And what's more, with the homomorphisms plus and minus, that one has naturality in this case. Now, down here is an isomorphism in quotation marks. Oh, come back. It is always surjective, definitely. There are nice and almost always satisfied conditions under which this is an isomorphism, but it's a little bit technical. Whew, are you tired yet? What is it? Oh gosh, it's time and I'm pretty tired. So let's wrap things up. To put everything together, to say what are the flows? So that the flows are precisely the homology classes of your graph with coefficients in the capacity sheaf. The values wind up being the image of H0 supported a cut, let's say, in the sheaf in H upper 1 compactly supported of the complement of your feedback edge. Gap is induced by the connecting homomorphism and the inclusion map of C into X. Now, the real killer inside of this is how do you define the homotopy limit in order to take advantage of the Poincare duality and get the theoretic MAXFLOW-MINCUT theorem. I'm afraid there's too little room in the margin to properly define the homotopy limit. I will say one word, like I will say con. That's it. It's going to be a right con extension. You're going to have to talk to COSHEAFI for the details on that one. All right. In the end, what do you do? You start off thinking in terms of a limit over some cut diagram. And maybe it's best to just do a simple example. Let's say that this is our feedback edge that goes this way from source over to the target. And this is really simple, but yet there are a lot of different cuts that you could choose that consist of both edges and collections of vertices and edges. And what to do is take a limit and then a homotopy limit over this diagram, looking at associated cut values. And then finally, you do so, you get to that chief theoretic MAXFLOW-MINCUT theorem, which constraints on time. I will not repeat the statement of. It's telling you that the feasible values, that H lower 1, is really the same thing as a homotopy limit of your values. All right. Why go to all this trouble? And it's a lot of trouble. Well, there's a couple reasons why. One is that there are lots of extensions that follow from this. We apply MAXFLOW-MINCUT type thinking to flows that involve, let's say, semi-modules of logical expressions instead of numbers. We can look at semi-modules of distributions, such as probability distributions. That's going to be very cool. You can apply MAXFLOW-MINCUT type thinking to this and a whole bunch of other related shows that are totally not applicable about the ordinary theorem. The second reason why is it gives us some insight into duality gaps. If you look at the literature, there's a huge literature on scenarios where when you have more than just a single commodity, the gaps between the maximal flow and the minimal cut. And the high-level idea is that duality gaps are really a feature of a homotopy limit to be the same thing at a limit. And if you understand things are the same and when different, then you have a lot of explanatory power. The reason to do this, the one that I really like the most, is that it's an excellent example of categorification. I wonder if I can spell that in real time. In that, it's not just one number equal to another number. It's rather this lifted semi-module is equal to this lifted semi-module. And that is the kind of thing that had a big impact in topology and I hope will have a big impact in applications. The challenges ahead, the first is to write down some nice examples. We have examples that are not so nice. Why they're not so nice is that it is very difficult to compute anything when you're talking about a homotopy limit. In a case where it has something very numerical, lattices, working with cancellative monoids, then not so bad. But in the general case, there's really no hope of getting good general algorithms. That's a challenge. We are out of time, and so with that, I am going to stop and refer you to Sanjeevi's paper, which he assures me is coming out on the archive tomorrow. Clapping for myself, and maybe somewhere out in cyberspace, someone is clapping.
Hey, Rob. Hey. So Rob has told us he has a little bit of time for questions. So if anybody has questions, unmute yourself and go ahead and ask Rob.
None.
All right, so I was going to ask you about the computational aspect, but you kind of said a little bit about that. One question is, at the beginning you mentioned other generalizations of MAXFLOW-MINCUT. This ones, does this kind of generalization have any connections to those generalizations using like matroids or algebraic ideas from algebraic geometry?
So the most general version I'm aware of is the version due to Freeze that works for total ordered commutative cancellative monoids. Wow, that's a mouthful. And it really requires that that total ordering. KRISHNAN does is things. Get rid of that requirement that things be totally ordered and allows you to work in a partially ordered setting. Now, free result is explicitly numerical, and KRISHNAN's result is not. You're going to get a semi-module of feasible flows rather than one maximal flow that you would get if everything was totally ordered. I have a question that popped up. Ask Gideon, do you have any examples in mind in the case that X is not just one-dimensional? Yes. What a great question. Indeed, one of the initial motivations for doing this using sheaves, because of course, sheaves will work over higher dimensional base spaces. Earlier in this project, we were very optimistic that we were going to be able to do this over arbitrary dimension base spaces and essentially take over the world. Those plans are a little bit on hold. It turned out to be a lot harder than anyone anticipated to get the theory with SEMMODULES to work on a one-dimensional base space. Sanjeevi has some preliminary results of getting it to work on higher dimensional base spaces. At this time, we're not claiming anything about MAXFLOW-MINCUT over high dimensions. Now, my graduate student, Greg Henselman, has some interesting preliminary results looking at MAXFLOW-MINCUT for higher dimensional simplicial complexes. They're not using this technology. That's a more limited, and Sanjeevi's got a ton of great ideas about how to get this stuff to work over higher dimensional complexes, but some restrictions over what is going to be possible. You need to have a directedness in order for this to happen, and it seems as though a cubical structure is going to be, if necessary, then at least very helpful. Or any other questions, I'd just like to remind you of our sponsor. One get through an hour-long talk at a camera. Why? Let's see, we've got another question from Gideon. Why is the simplicial structure not enough in the higher dimensional setting? Whew, you don't want me to answer that. Directedness. So all of cohomology theories are really taking advantage of the directedness. Directed topology on a simplicial complex gets very messy very quickly. It's easier to put a directedness on a cubical complex because you can choose basis directions and say this is forward and this is forward. My level of understanding as to why cubical directed spaces are nicer than simplicial. Sharing my desktop, so I think I'm going to stop sharing. That way you can look at my question. My window is not quite up.
So saying that the hope for extending the theory to higher dimensions using cubical complexes?
And for Sanjeevi, in terms of what he thinks is possible, I'm in the dimensional world until I get a really clean set of simple examples to illustrate what's happening. Difficult enough to and talk about this stuff and compute examples over a one-dimensional base space. Higher base spaces, difficult.
Questions to developing a calculational version of this theory are to do with calculating homotopy colimits.
Homotopy limit.
Right.
It's a homotopy limit.
And it's difficulty because of the break structure, or just?
Yes. So the fact that the diagrams over which you're taking these can get quite large. If you have a realistic graph, there's a lot of different cuts that you have to look at. And if the computation of cut values is more involved than just adding up some numbers, which case it is, then that is computationally formidable. Provably so, in the modest setting of multi-flows, which falls under the aegis of looking at modules, then there are results that show that trying to compute the MAXFLOW or the MINCUT is NP hard, so it's not going to be a fast algorithm for it. That there are analysts of some of the standard algorithms for Wilkerson, push relay, that up to this categorical or module setting. There are steps in there, however, that are computationally and algebraically very challenging. videotaped, right? So watching me. Nice. How's my hair? Yeah. All right.
All right. Any questions? Let's maybe I'll thank Rob. So stay tuned.
Claps. Love the Thank you very much. Thank you very much.
All right, so thank you to everybody for participating, and I think, so again, Rob, for helping us. I think technically it was a bit of a challenge, and I think things worked out great. I think to help. So this week, Shmuel Weinberger will be giving us a talk